welcome to this problem walkthrough. Today, we'll explore LeetCode problem number 1886, determine whether matrix can be obtained by rotation. In this problem, we'll examine how to determine if one matrix can be transformed into another by rotating it 90, 180, or 270 degrees. Let's dive in. In this problem, we are working with two and binary matrices, mat and target. The goal is to determine if it's possible to make mat equal to target by performing 0 or more rotations of mat. Each rotation involves turning mat 90 degrees clockwise. If mat can be transformed into target through one or more rotations, we return true, otherwise, we return false. The input consists of two binary matrices, where each cell contains either a 0 or a 1. The output is a Boolean value, either true or false, based on whether the transformation is achievable. Now, let's look at some examples to better understand how this works. Here's the first example. We're given mat as 0, 1, 1, 0, and target as 1, 0, 0, 1. Initially, mat and target are not the same. However, if we rotate mat 90 degrees clockwise, it becomes 1, 0, 0, 1. This matches the target matrix, so the output for this example is true. This demonstrates that a single rotation is sufficient to transform mat into target in this case. In the second example, mat is 0, 1, 1, 1, and target is 1, 0, 0, 1. After the first 90-degree clockwise rotation, mat becomes 1, 0, 1, 1. This does not match target, so we rotate it again. After a second rotation, mat becomes 1, 1, 0, 1. Still, this does not match target. Let's see what happens when we continue rotating. After a third rotation, mat becomes 0, 1, 1, 0. Even though we've now tried 3 different rotations, none of these match the target. After the fourth and final rotation, mat returns to its original configuration, 0, 1, 1, 1, which still doesn't match target. Since none of the rotations result in mat equaling target, the output is false for this example. In the third example, mat is 1, 1, 0, 1, and target is also 1, 1, 0, 1. In this case, mat is already equal to target, so no rotations are needed. As a result, the output is true. The constraints for this problem include ensuring that both matrices are square and of the same size, with dimensions ranging from 1 by 1 to 10 by 10. It's important to handle edge cases, such as when no rotations are needed, when matrices are of the smallest or largest possible size, and when all 4 rotations fail to produce a match. Keeping these scenarios in mind ensures we create an efficient solution that correctly handles all inputs. To solve the problem of determining whether the matrix mat can be transformed into target through rotations, we considered several approaches. The first is the brute force method. The intuition behind this approach is straightforward. Since there are only 4 possible orientations of mat, 0 degrees, 90 degrees, 180 degrees, and 270 degrees clockwise, we can systematically check if target matches mat in any of these orientations. Here's how it works. We start with the original mat and apply a 90-degree clockwise rotation to generate a new matrix. After each rotation, we compare the resulting matrix with target. If any of the comparisons match, we return true. Otherwise, after checking all 4 orientations, we return false. In terms of complexity, rotating an NXN matrix requires n squared, time to traverse and reposition elements, and comparing 2 matrices also takes n squared. Since we repeat this process up to 4 times, the overall time complexity is for n squared, which simplifies to n squared. The trade-offs of this approach include its simplicity and efficiency for small matrices, making it well suited for problems like this where n is relatively small. Another approach we considered is optimized rotation comparison. The intuition here is to avoid creating new matrices for each rotation, which can save memory. Instead, we calculate the indices of elements in mat that correspond to their positions in target after rotation and compare them directly. For each potential rotation, 0 degrees, 90 degrees, 180 degrees, and 270 degrees, we map the indices of mat to their corresponding positions in target and check if all elements match. If any rotation matches, we return true, otherwise, we return false. The time complexity remains n squared, because we still need to traverse and compare all elements for up to 4 rotations. However, this method is more space efficient since it avoids creating new matrices. The trade-off is that this approach is slightly more complex to implement due to the need for calculating rotated indices. Additionally, we explored an early exit optimization. The idea here is to stop checking a rotation as soon as a mismatch is found. During each rotation comparison, if a mismatch is detected while traversing the matrix, we immediately stop and move to the next rotation. This reduces unnecessary computations in practice, although the worst-case time complexity remains n squared, since we might still need to check all 4 rotations if mismatches occur late in the traversal. This method can improve efficiency in scenarios where mismatches are detected early, but it adds another layer of logic to the implementation. Given the options, we chose the brute force approach with incremental rotations. This method stands out because it is simple, intuitive, and efficient given the constraints of this problem. Since there are only 4 possible rotations and the matrix dimensions are relatively small, the overhead of creating new matrices is negligible. Additionally, the brute force method is easier to implement and debug compared to the optimized in-place comparison approach. A key observation that supports this choice is that there are only 4 orientations of MAT to consider. This drastically limits the complexity of the problem and makes it feasible to explicitly generate and compare all 4 rotations. The realization that matrix rotation is deterministic, and that we can systematically generate all orientations of MAT, simplifies the problem even further. This eliminates the need for advanced algorithms or backtracking, making the brute force approach a practical and effective solution for this scenario. When comparing the approaches, we see some clear trade-offs. The brute force method is easy to implement and debug but uses slightly more memory because it creates new matrices for each rotation. On the other hand, the optimized rotation comparison saves memory by avoiding new matrix creation, but it is harder to implement and debug due to the complexity of calculating rotated indices. The early exit optimization can help reduce computations in practice by stopping when mismatches are detected early, but it does not improve the worst-case time complexity. Considering the constraints of the problem, the brute force approach strikes the best balance between simplicity and efficiency. Its n squared time complexity is acceptable given the small matrix size, and its straightforward implementation makes it a practical and maintainable solution for this problem. To solve this problem, we need to determine if the matrix MAT can be transformed into the matrix target using 1 or more 90-degree clockwise rotations. The first step is understanding the size and structure of the matrices. Both MAT and target are square matrices of size nxn, meaning the number of rows equals the number of columns. Since the problem guarantees valid inputs, we can assume the dimensions are identical. Next, we define a helper function to perform a 90-degree clockwise rotation. The key idea is to remap the element at position I, j, in the original matrix to position j, n1i, in the rotated matrix. To make this process simpler, we create a new matrix to store the rotated result rather than modifying the input matrix in place. This avoids unnecessary complications and keeps the implementation clean. The provided Python function, rotate_clockwise, achieves this by iterating through the rows and columns of the input matrix and populating the new matrix with the rotated values. Once we have the rotation function, we proceed to iterate through the possible rotations. These include the original matrix, 90 degrees, 180 degrees, and 270 degrees clockwise. For each step, we start with the current version of MAT, and after each rotation, we compare it with the target matrix. If the rotated matrix matches target at any point, we can immediately return true. This means MAT can indeed be transformed into target with the specified rotations. If none of the rotations produce a match, we return false. The Python implementation of the findRotation function encapsulates this logic. It iterates up to 4 times, checking the equality of the matrices after each rotation. The early return ensures that we save computation time by stopping as soon as a match is found. Now, let's break down the key insights of this algorithm. First, the matrix rotation itself is based on swapping rows and columns with adjustments to maintain the correct indices. Specifically, the transformation of I, j, to j, n1i ensures that the elements are repositioned correctly for a clockwise rotation. Using a helper function to handle this transformation simplifies the process and avoids the complexities of in-place rotation. In terms of efficiency, the algorithm is highly optimized. Each rotation and comparison operates in n squared time, where n is the matrix size. Since we perform at most 4 rotations, the overall time complexity remains n squared. Additionally, the equality check between two matrices is efficient, as it runs in n squared as well. An important optimization is the early exit condition. If a match is found at any stage, the algorithm stops further rotations, saving unnecessary computations. From a data structure perspective, the algorithm relies on representing mat and target as 2D arrays, or lists of lists in Python. For each rotation, a new intermediate matrix is created to store the transformed values. This ensures that the original mat remains intact and can be used for subsequent rotations. Edge cases are also worth considering. For instance, if mat and target are already identical, the algorithm returns true immediately without performing any rotations. On the other hand, if the matrices are completely different, all 4 rotations will be checked before returning false. Single-element matrices, such as a 1x1 matrix, are another edge case. Since such matrices remain unchanged after any rotation, the algorithm correctly identifies them as matches. These considerations ensure the algorithm handles a wide range of input scenarios effectively. Finally, let's touch on symmetric matrices and key optimizations. Symmetric matrices, which look the same after certain rotations, are still accurately handled by the algorithm. For example, a 2x2 matrix with all identical elements will always match itself, regardless of rotation. This is because the algorithm checks every rotation systematically. In terms of optimizations, the algorithm minimizes the number of rotations by exiting early when a match is found. This not only reduces computational overhead but also ensures the solution is efficient. Additionally, avoiding redundant checks after a match prevents unnecessary processing. Together, these optimizations strike a balance between simplicity, clarity, and performance, making the algorithm robust and efficient for solving the problem. The provided solution determines whether the matrix mat can be transformed into the matrix target through one or more 90-degree clockwise rotations. Here's a detailed explanation. 1. Helper function rotate. This function performs a 90-degree clockwise rotation of the input matrix. For each element in the matrix, it maps its new position using the formula, matrix n1j I. Here, n is the size of the matrix, I is the row index, and j is the column index. A new matrix is constructed via list comprehension to reflect the rotated state. 2. Outer loop. The main function performs up to 4 rotations, 0, 90, 180, 270 degrees, since any square matrix will return to its original orientation after 4 rotations. After each rotation, the rotated mat is compared to target. If they match, the function immediately returns true. If none of the rotations match target, the function returns false after all iterations. 3. Efficiency. The function uses a nested list comprehension for rotation, which operates in n squared time for each rotation, where n is the matrix size. Since there are at most 4 rotations, the total complexity is for n squared equals n squared. 4. Edge cases. An already matching mat and target is handled by the initial comparison. All valid square matrices are supported, as the algorithm assumes mat and target are of the same size. This solution is concise and effective for the problem requirements, ensuring correctness across all possible inputs. Here, we begin by defining a Java class called solution and the main method findRotation, which takes 2 integer matrices, mat and target, as input. The goal is to determine if the matrix mat can be transformed into the target matrix by rotating it in 90-degree increments. First, we calculate the size of the matrix n, since the matrices are square. Next, we define a helper method called rotate, which performs a 90-degree clockwise rotation of the given matrix. This is done by creating a new 2D array, rotated, and populating it by mapping the rows and columns of the original matrix to their new positions after rotation. Specifically, the element at position I, j, in the original matrix is moved to j, n1i, in the rotated matrix. Once the rotation is complete, the method returns the newly rotated matrix. Afterward, we use a loop to check all 4 possible rotations of the input matrix. If, at any rotation, the current matrix matches the target matrix, we return true. Otherwise, we continue rotating the matrix and rechecking. To check if 2 matrices are equal, we use a helper method called rMatricesEqual. This method compares the 2 matrices, mat1 and mat2, element by element. It iterates through each row and column using nested loops. If it encounters any element at position i, j, in mat1 that does not match the corresponding element in mat2, it immediately returns false, indicating that the matrices are not equal. If all elements match across both matrices, the method returns true. By combining this equality check with the rotation logic, the program ensures that it will correctly determine whether the target matrix can be obtained by rotating the input matrix in one of the 4 possible orientations. In this example, we start by checking if the given matrix mat matches the target matrix target. Initially, mat is 0, 1, 1, 0, and target is 1, 0, 0, 1. These matrices are not equal, so we proceed to the next step. Now, we perform the first rotation of mat by 90 degrees clockwise. To do this, for each column in the original matrix, we create a new row in the rotated matrix by taking the elements from bottom to top. After this rotation, the matrix becomes 1, 0, 0, 1. Comparing this rotated matrix with target, we see that they are now equal. Since we've achieved a match, we return true as the output for this example. Here, we consider a case where no match is achieved even after 4 rotations. The initial matrices are mat equals 0, 0, 1, 1, and target equals 1, 0, 0, 1. A comparison shows they are not equal. We then perform the first rotation on mat, which results in 1, 0, 1, 0. Comparing this rotated matrix with target, we find no match. Next, we rotate mat again, resulting in 1, 1, 0, 0. Once more, the rotated matrix does not match the target, so we proceed further. Continuing, we perform the third rotation on mat, which results in 0, 1, 0, 1. Comparing this matrix with target, we still do not find a match. Finally, we rotate mat a 4th time, bringing it back to its original configuration of 0, 0, 1, 1. Comparing this with target, we again find no match. Since we've completed 4 rotations and none of them produced a match, we conclude that it is not possible to transform mat into target through rotations. Therefore, we return false as the output for this example. Next, let's consider another example where a match is achieved after multiple rotations. In this example, we begin with mat equals 1, 0, 0, 0, and target equals 0, 0, 0, 1. A comparison shows that they are not equal, so we move forward. First, we rotate mat by 90 degrees clockwise, resulting in 0, 1, 0, 0. Comparing this rotated matrix with target, there is no match. Then, we perform a second rotation, which gives us 0, 0, 0, 1. This time, the rotated matrix matches target. Since we've achieved a match, we return true as the output for this example. This demonstrates that a match can be found at any point within the 4 rotations. To summarize, the solution involves rotating the matrix mat up to 4 times, or a full 360 degrees, and comparing it with the target matrix target after each rotation. If a match is found at any step, the function returns true. On the other hand, if all 4 rotations are completed and no match is found, the function returns false. This approach ensures that we exhaust all possible orientations of the matrix before concluding whether or not it can be transformed into the target. To analyze the time complexity of our solution, we need to evaluate each of its core steps. First, consider the rotate function. When we rotate an nxn matrix, we need to reposition each of its n superscript 2 elements to their new locations in the rotated matrix. This means that a single rotation operation has a time complexity of O, n superscript 2. Next, we compare the matrix mat with target using the equality operator. This comparison involves checking each of the n superscript 2 elements in the matrices, which also takes O, n superscript 2, time. Finally, the algorithm uses an outer loop that iterates up to 4 times, once for each possible rotation. During each iteration, we perform one matrix comparison and one rotation, both of which are O, n superscript 2, operations. This means that each iteration of the loop has a total time cost of O, n superscript 2, plus O, n superscript 2, which simplifies to O, n superscript 2. Now, combining all of these steps, the overall time complexity of the algorithm can be determined. In the worst-case scenario, the algorithm might need to perform all 4 rotations and corresponding comparisons. Since each iteration has a time cost of O, n superscript 2, and there are at most 4 iterations, the total worst-case time complexity becomes 4 asterisk O, n superscript 2, which simplifies to O, n superscript 2. Moving on to space complexity, let's analyze the additional space requirements of the algorithm. The rotate function creates a new nxn matrix during each rotation, which requires O, n superscript 2, space. Besides this, the algorithm uses a few additional variables, such as n and the loop counter, which take up constant space, or O1. Therefore, the overall space complexity is dominated by the creation of the rotated matrix, which means the space complexity is O, n superscript 2. When comparing this approach to a naive solution, the benefits of the current solution become clear. A naive approach might pre-compute all 4 possible rotations of the matrix before starting the comparison process. This would still require 4 asterisk O, n superscript 2, or O, n superscript 2, time to generate the rotations, but it would also use additional space to store all these rotations. Specifically, storing the 4 rotated matrices would require O, for asterisk n superscript 2, which simplifies to O, n superscript 2, space. In contrast, the optimized approach we're discussing avoids pre-computing all the rotations. Instead, it computes and compares one rotation at a time, discarding the previous rotation before creating the next. This reduces space usage to O, n superscript 2, matching the time complexity and making the solution both time efficient and space efficient. Let's evaluate the algorithm under different scenarios to understand its best case, average case, and worst case performance. The best case occurs when MAT already matches target without requiring any rotations. In this situation, the algorithm performs a single comparison with no rotations, resulting in a time complexity of O, n superscript 2. In the average case, the algorithm might need to perform around 2 rotations before finding a match or determining that no match exists. This results in a time complexity of approximately 2 asterisk O, n superscript 2, which simplifies to O, n superscript 2. Finally, in the worst case, the algorithm performs all 4 rotations and finds that none of them match target. Here, the time complexity reaches its maximum value of 4 asterisk O, n superscript 2, which simplifies to O, n superscript 2. To conclude, let's confirm the big O complexities of this algorithm. Both key operations, rotation and comparison, scale quadratically with the size of the matrix, since they involve iterating through all n superscript 2 elements. With the outer loop running a fixed number of times, specifically 4, the total time complexity becomes 4 asterisk O, n superscript 2, which simplifies to O, n superscript 2. For space complexity, the dominating factor is the creation of a new rotated matrix during each call to rotate. Since only one matrix is created at a time, and no additional large data structures are used, the space complexity is O, n superscript 2. In summary, the final complexities of this algorithm are O, n superscript 2, for both time and space. When tackling this problem, there are several common pitfalls to watch out for. First, many people forget to check if the matrix already matches the target without any rotation. This is the 0-degree rotation check, and skipping it can lead to incorrect results. Next, modifying the original matrix directly while attempting rotations is another frequent mistake. This can cause issues if you need to perform multiple rotations since the original data might be overwritten. Instead, it's better to use a helper function that generates new rotated versions. Another area where errors occur is in the rotation logic itself. For a 90-degree clockwise rotation, the indices change in a specific way. The new value at position rotated, I, j, comes from mat, and j1, I, in the original matrix. Misunderstanding or misapplying this formula often leads to incorrect outputs. Lastly, some people overcomplicate the problem by handling non-square matrices, even though the problem guarantees that both matrices are square. Keeping this in mind can help avoid unnecessary effort. Efficient matrix comparison is another important consideration. Instead of manually comparing elements in nested loops, you can take advantage of Python's == operator or similar options in other languages to directly compare two matrices. This is both concise and efficient. Now, thinking about interviews, this problem is a great example of combining array manipulation with matrix transformations, which are common themes in technical interviews. You should be comfortable with rotating matrices both clockwise and counterclockwise, as these are fundamental operations. Pay special attention to edge cases, such as when mat is identical to target without any rotation, or when no rotation can make the matrices match. It's also worth noting that you only need to try up to 3 rotations, since the fourth would return the matrix to its original position. To optimize your solution, stop as soon as a match is found. There's no need to check further rotations. Using helper functions can also make your code clearer and easier to debug. This problem connects to several related LeetCode challenges that can help deepen your understanding. For example, LeetCode number 48, Rotate Image, focuses on rotating a matrix 90 degrees in place, which is closely tied to the rotation logic we use here. LeetCode number 796, Rotate String, shifts the focus to string rotations, but the underlying concept of transformations applies. LeetCode number 867, Transpose Matrix, is a simpler problem involving basic matrix manipulation, and LeetCode number 54, Spiral Matrix, explores traversing a matrix in a spiral order. These are all worth exploring as they reinforce similar skills. In terms of alternative approaches, you could choose to perform rotations in place instead of generating new matrices. While this reduces space complexity, it introduces a higher risk of overwriting data incorrectly, so it requires careful implementation. Another approach is to pre-compute all 4 possible rotations of the matrix and store them. This simplifies the comparison logic but increases memory usage. Another optimization you might consider is matrix hashing. This involves converting each matrix into a hashable format, such as a string representation, and storing all 4 rotations in a set. Then, you can simply check if the hash of the target matrix exists in the set of pre-computed rotations. This method is particularly useful if you need to perform repeated checks, as it allows for fast lookups. However, it does involve some pre-processing overhead, so it's important to weigh the trade-offs based on the specific problem requirements. Overall, this hashing technique offers an efficient way to handle the problem, especially in scenarios where multiple comparisons are needed. Great job! In this session, we tackled matrix rotations and covered an efficient way to determine if one matrix can match another. Remember, practicing matrix problems strengthens your understanding of 2D data structures. Thanks for tuning in, and be sure to check out more problems to keep improving your skills. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!